So we're in 11.1. 11.1 is goodness. There it is. Goodness of fit. So what you need to do? What you need to do a lot of times in a real life situation is see if these numbers fit with what Benford's law predicts the leading digits should be. So are the leading numbers fitting what they should be for the inner arrival times on the internet, for the times between arrivals on the internet? Or, if not, you think that the thing's been hacked. The times are funny, they've been hacked. It's hard for hackers to get around Benford's law. That's why this is pretty effective virus protection, because it's very difficult for a hacking system to exactly imitate Benford's law and make its times fit that. So it's a great tool. It's a great way to block the hackers. So here we go. How do we do it? Well, what we've got, this is observed. These numbers are observed. That's what we actually saw. We observed 76 times. The leading number was a 1. Again, they're not showing us the numbers. The numbers might be, like the arrival, the times between arrivals might be, 186 seconds, 293, 114, 862. I don't know, but the leading digits is all, I don't even know what the times are, but I know that 76 times the leading digit was a 1. 62 times the leading digit was a 2, etc. You tracking with me? Understand what that data in that table means? Yep. So there was a whole bunch of numbers, and 76 of them had a leading digit of 1, 62 had a leading digit of 2, etc. Does it fit Benford's law? Well, you need the observed numbers. There they are. That's what was observed. That's what the computer recorded. Now, you also need to compare that with the expected numbers. How do we get the expected? We're going to put them down here. Got to get some of this stuff out of the way. We need the expected numbers. So they're going to go down here. So how do we find them? How many numbers with a leading digit of 1 did we expect? We got 76, right? That's what actually happened. 76 numbers with a 1 in front were recorded. 62 numbers with a 2 in front, etc. Well, how many did we? If Benford's law was being followed, then how many did we expect right here? We got 76. How many should we have got? If Benford's law is being perfectly followed, how many should we have received? Remember we talked about expected? Let me ask this. If I said there were 100 babies, right, remember it's all coming back now, right? So remember I said if you had 100 babies and were born in some city in New York over the weekend, how many girls would you expect? 50. And how are you coming up with that number? You're taking 0.5 times 100. I mean, I know you're just doing 50 off the top of your head, but that's the calculation that would do it, right? You would just take the percentage, like the point. You're going to change this to a decimal, right? 0.301. Make that a decimal. Because 30%, like 50% is 0.5. 50% girls, right? 30.1% numbers with a front digit of 1. So make that a decimal, 0.301 times. What if there were 200 babies born 200 babies born in California over the weekend? We would just multiply 0.5 times 200. Half of 200, 100, right? 75. Right, we get? So my point is you would multiply the percentage times the total number. It's percent times total number. How are we doing? Am I making any sense? I'm looking into your eyes for understanding. So to figure out expected, let me make this more clear. So to figure out expected, just like we did 0.5 times 200 babies born in California over the weekend, 0.5 times that we would expect that would equal 100 girls, right? So you need to take the percentage times the total number And that gives you what you expect. So the same thing will work for any time we have an expected whatever. This section's a lot about that. So, okay, so if...
Kind of like the total number, like with the bottom numbers, all of them?
That's it. Exactly, Eddie. Yeah, right on. We need to total all those numbers.
Which is what, 317, is it?
Yep.
Oh, great. Yeah, thank you. I didn't even notice that. Yeah, 317 numbers. So yeah, that must be the total of all those things. Thanks, great. We already got the total. I was going to add them up. So I think I did last time, didn't I? Anyway, 317. So we got the total. So there's 317 numbers, right? 76 of them have a 1 in front, 62 have a 2 in front, etc. We're not even seeing those numbers. We don't want to see those numbers. But there's 317 numbers. So if there's 317 total numbers, how many would Benford's law tell us we should expect have a 1 in front? Well, 30.1% of them.
95.417.
Yeah, and so what we do is we come over here and we just say, okay, if you want to know how many you should expect from Bedford's law, expected number, yeah, you just take 0.301 times 76. What is it again, Val?
Is it 76 or 317?
Oh, you're right. 317. I'm being crazy. All right, thanks. What do you got?
95.417.
95.417. Is that making sense?
Do we gotta do that for each one?
Yeah, kind of tedious, huh?
So then it's-
Now, we're not going to really do this. They've actually done it for us in this problem. So I'm not going to do any more. But that is what we'll do in the other problems when we have to do it. Now, what I mean by they've done it for us, they're going to just jump us to the final answer, because this is just the first problem and they're just getting us warmed up. But that would be what we would have to do. And then we would put all these numbers in L1 and all the expected numbers in L2, and then we do our thing on a calculator. I'll show you as we get to it. But so we're not going to do any more. That's what we would have to do. So let me now write out for you the null. So we're in 11.1, goodness of fit. And the null hypothesis in the goodness of fit section is always that the two data sets fit, that they do fit, that they're basically the same. And the alternative, what's the alternative then? They don't fit. They do not fit. They're different. And that'll always be the null and the alternative. You don't have to write anything or worry about anything else. So this section, goodness of fit, the null is that it's a good fit. And the alternative is it's not a good fit. So, all right. So every time that's going to be the null and the alternative. And then basically I'll write out some more instructions in a minute. Let's just get back to the question. So they're saying, so again, I'm not going to calculate all those. They're just wanting me to give the correct null and alternative. So what is it? This null, if you can see it, all those numbers, this says P1 is 0.301. That's right. P2 is that. That's right. P3, etc. That's what the null says. That's a fit.
Right.
And the alternative, at least one of them is not equal, does not fit. That's exactly right. So A is the right one. Why are the other ones wrong? Well, B's got them reversed. Is this making sense? The null hypothesis is supposed to say that the proportions end up fitting Bedford's law. So the null on A is the right answer. It says they fit. B says at least one of them is not equal, doesn't fit. Right. That's how you do the null and alternative for a goodness of fit test. B is wrong. They've got them swapped. What's wrong with C? Oh, it says none of them. None of them are equal. No. It's not about like all or none. If you just have one digit off pretty badly, that'll break it. So A is the right answer. At least one is not equal. It's not D. It says at least one is different from the others. No, we're not comparing them with each other. We're comparing them with the law. No, that's right. Anyway, so we got it. Let's move on. So setup and the conclusion without having to do the buttons in between for this one. So now finishing up the problem, we just did the Benford's Law problem. They're saying, all right, let's get an answer. Suppose you did it on your calculator, and here's the answers you got from Benford's Law. What do you think? We're going to keep the null or not? Look at that p-value. So we got a p-value of 0.0074. Is that? That's a low one, right? That's less than 0.05. The p is indeed low. So reject the null, or the null must go. That's right, that's how we say it. I forgot our saying. P is low, the null must go. So we're going to reject the null. What was the null? The two data sets fit. Reject. We reject that. So what do we believe? Don't fit. We believe that something in what's coming down the line from the computer, something doesn't fit. At least one of them, maybe more, of those leading digit counts is off. Considerably off. Strong evidence, right? That's a really low p-value. Whenever you go with the H1, you know that always means strong evidence, huh? So there must be strong evidence that something doesn't fit. Something doesn't fit. So that would tell them, you better look for a hacker. Right? The internet times are considerably off of what Benford's Law predicts you're normally going to see. So can we write in those little words? Let's see. Because the leading digit of inner arrival times do not fit, right? That was our conclusion. Let me write it here. I should have written it down here. H1. Do not fit. That was our H1 right there, right? Don't fit. All right? Does not fit the distribution described by Benford's Law. It appears that those times, what? Are or are not typical? Are not typical. They're not what you would normally see. There is a good chance or very little chance? A good chance that the computer has been hacked. Corrective action is needed. Make sense? The rest of the problems we'll do ourselves on the computer. The calculator. So they just wanted us to get us warmed up on seeing how you set these things up, a goodness of fit test, and how you wrap them up. And really, they're pretty straight ahead. It's just HO they fit, H1 they don't. All right. Let's dive in. All right. Number 3. A police department released the numbers of calls for the different days of the week during the month of October, as shown in the table to the right. Use the pointer one to test claim that the different days of the week have the same frequency of police calls. What's the fundamental error with this analysis? Okay, so basically they're saying, do the same day, does every day of the week have the same number of police calls?
No.
Yeah, no way, huh? But let's go through and do the formal. It's kind of a silly question, but we'll go through, do the formal analysis. So how do we do it? The claim is the days are the same. So, see these frequencies right here? That's what actually happened during the month of October. 160 police calls on the different Sundays in the month of October, 206 on Mondays, 222 on Tuesdays, etc. So, are those numbers observed or predicted? Observed or expected? They're observed, right? That's what they actually saw happen. Not what they were thinking was going to happen, not expected, but what they actually saw happen. This is observed. Those are the observed numbers. So you always, on these goodness of fit tests, you always need observed and expected. So there's observed. Now, can we calculate the expected? That's going to be the hard part of goodness of fit, because it's going to be a little different from problem to problem. It's not always the same. It's not just one size fits all. It's going to be a little different from example to example. So, any thoughts? If the days were really the same number of calls, Sunday, Monday, Tuesday, Wednesday, well then what would we have expected to see? How do we figure that out?
You just add them all and then divide them
Exactly.
by the number there is, and then that will
That's it.
solve it.
That's it. Leonardo's got it. Does that make sense? Just add them all up, get the total number of calls, and then divide by what? How many days in the week? 7. They should each have 1/7, right? Does that make sense? That's what we would expect if it was all the same. How are we doing? Am I making any sense?
Yes.
Good? How you guys doing? You guys are good students to be here at 7 o'clock at night, week after week after week. Are you tired? I'm sure you are. But I'm glad you're committed, and you guys are impressive. All right, to keep coming and coming and coming. 2 more weeks, you're free. All right, so let's add them all up. Let's add them all up. So you guys, somebody have a calculator? Maybe somebody, while I was talking, somebody already added those up. Good. What is it?
I think 1445.
Anybody else got that same number? Sounds good to me. All right, good, thanks. So that's the total. Just added those up. Now, just divide by 7, right? Because each of those will take 1, 4, 4, 5, and divide by 7. And I'm getting 206 point. Now, I don't know how far we should go, honestly. Oh, does it? Where's it say? Oh, yeah, Dad, the final thing, yeah. I don't know what to do in between. How about I just go 4, 3. Let's round to 2 play. Well, maybe I better do 3, huh? Yeah, I don't know. 4, 2, 8, 4, 2, 9. How about that? 206, 4, 2, 9. That means there, and there, and there, all those, right, are what we would expect that many calls on each day. Because if all the days were going to be the same, now first off, I think that's part of what's, well, we'll get, how can you have part of a call? I mean, what's 0.429? But anyway, whatever, let's just run the numbers. We'll get back to that in a minute. That has to do with the fundamental error, but we'll get back to it. So is this making sense what I'm saying? The expected, that's how many calls you would expect. If all the days were going to be the same, then just take the total calls, divide by 7. You should have 206.429 every day. So now put into your calculator, take out your calculator, put in these numbers. The observed is L1. That's going to be L1. And L2 is expected, and all the expecteds are 206.429, 206.429, 206.429, all the way down the line.
So L1 is,
Once you've got it in there, we just do the test. We just hit Stat, go over to Tests, and select the chi-square GOF test. Goodness of fit. Now, that's for the people with the TI-84s.
is that why you had to, is that the thing that you like gave them the virus or no?
That's right. Exactly. And the categories. That's right. I forgot to say that. Yeah, I think you're right. Yeah, 6, right. Yeah, good question. DF, which is degrees of freedom, is N minus 1. So that's, 7 minus 1, 6, because there's 7 categories. It's number of categories minus 1, so it's going to be 6. So if you have this instructions I just gave right here, hit stat, test, GOF, and you got to put in degrees of freedom 6, because right here it's N minus 1. Degrees of freedom is always N minus 1, so 1 less than the category numbers. That's all for the TI-84 people. If you have a TI-83, it's actually, I just gave you the program, it's even easier. All you do for the TI-83 people is you hit program, the program button, which is right in the middle top, PRGM. Just hit program. And you'll see the program. Just hit enter a couple of times. It'll do it automatically. Don't even have to put in the degrees of freedom or anything.
What did you put on my calculator?
Crazy virus. All right. Is it working? So you should get a chi-square value. Let me see.
Excuse me.
You should get a chi-square value. Is it 26? 525?
Six.
Oh. I got 525.
Yeah, round up.
Round it. Mine was 5253. What'd you all get?
5258.
Oh. Okay. So 526. You're all right. I'm not sure why I'm getting off by one. P-value?
Probably put your number wrong.
Perhaps. Did you guys get a p-value 1.776?
P-value?
Yeah, but -4.
-4, so
So that's 0, 0, 0.
0.0002. Yeah. Getting that okay?
So reject the null.
Okay, so that's p-value. Yeah, oh, and I forgot to write in the null. What was the null? What's the null always in this section? It fits.
Fits.
Does not fit.
Is that what we have to put as answers?
Wait, so what did you get? How did you get 00 point or 002?
Yeah. The number was
There's an E4 at the end.
Okay, this is okay.
Yeah.
I got it.
1.77. Yeah, E minus 4. So remember what that E minus 4 means? Decimal back 4 places. We good with that? So when you take that 1.77 E minus 4, I'm running out of room here. E minus 4. 1.77 E minus 4. Decimal back 1 place, and then the other 3 bring in zeros. So it becomes 30177, which rounds to 0002, doesn't it? When we round 4 places. We good? So what does that mean? That's a low p-value. Low p-value. So what do? Reject the null. So P is low. Reject the null must go. If P is low, the null must go. Reject the null. So we believe the data does not fit. So reject the null. There it is, C, huh? Reject the null. There's sufficient evidence. So in other words, the police calls are not all the same for every day, of course. It's kind of a dumb question, huh? Of course, they're different for different days. Is that good? October has 31 days. 2 of the days of the week have to be more. You can't have an even number. Like if 7 days in the week, that would only work evenly if it was something like February, which has 28 days. Right? It could never work if you have 30 or 31 days. Right? If we had February, which had 28 days,
So it'd be 3 of the days.
then there could be 4 of every day because there's 4 weeks. There's exactly 4 weeks in February. 4 times 7, 28. But there's not exactly 4 weeks or 5 weeks in October, which has 31 days. So there's no way you're going to get the same number of calls when you have a month that doesn't have the same number of Sundays as Mondays as Tuesdays. That was really kind of a dumb question. Right?
So C.
So, well, actually, it's 3 of the days. Yeah, why? How'd you know, Val? It was 3.
Because there's 31 days in the month.
Right.
3 days is October. So
That's-
3 of them have one of them.
Exactly. Everybody see what Val's seeing? He's right on. Right? If there were 28 days, that would be 4 weeks exactly. But October has 31, so that's 3 more extra days. So that means there's 3 days that are going to have extra calls because they're in the month of October. That's why it was kind of a dumb question, really. Of course they're not going to come out the same. All right, how are we doing? Answer whatever question. Here's number 5. Let's try it. So we're talking about baseball. It's saying the table below lists the number of games played in a yearly best-of-7 baseball championship series, along with the expected proportions for the number of games played with teams of equal abilities. So in other words, what they're saying, if you got 2 teams that are pretty much even, Steven, isn't baseball funny that way? I think baseball is very funny in comparison to like football or basketball. The best teams in baseball, top teams, what's their winning percentage usually?
60 or something.
Yeah, like 60% usually, or 63. What's the worst team? It's usually like 35% or maybe 40. I mean, they're hardly different, right? I know, I just think baseball is funny. The worst team can beat the best like almost half the time. The difference is like 1 game out of 10. It's kind of funny. Whereas the best football team, they might only lose 1 game all season or 2. Right? Anyway, just different. Baseball is a different kind. Everything's very even, Steven. So in baseball, if the 2 teams are very even, Steven, then 2/16 of the time, that's expected, you would expect that the series would go in 4 games. Somebody would sweep in 4 straight games. And 4/16 of the time, they calculated these with probability. You would expect the series to last 5 games. Somebody wins 4 games to 1. 5/16 of the time, the series would last 6 games. And 5/16 of the time, the series would go to the 7th game. If the 2 teams were even Steven. That would actually work for baseball or basketball. Any 2 teams that are even Steven. Those are the probabilities of the various amounts of games that would be played. Now, they're saying, okay, so what's the actual contest? What happens? So here they have a record for baseball for, I don't know, the last whatever years. 18 World Series were ended in 4 games. 22 series went 5 games. 23 went 6 games. 36 World Series lasted 7 games. That's like the last 100 years of baseball, basically. How we doing?
Bad.
All right. So what's the greatest baseball team ever?
Giants.
No, we're not talking about our warm fuzzy feelings. We're talking about the hard, cold numbers. Clearly the Yankees, right? I mean, much as I hate them, they have got the dominance of total titles and.
Yankees?
Oh yeah, the Yankees for sure.
Not Red Sox?
No, Yankees have. Yeah, Red Sox have been rising up, but the Yankees historically have won way more. They won the World Series way back in the 20s. They won it 5 years in a row. You know that? You know, I was into baseball when I was a kid. What's that?
There was only 3 teams then.
It was easy. They were all Little League, you know? All right. Anyway, let's get on with this problem. So how do we solve this problem? We've got it. These expected, these are just like percentages. They're fractions, but same thing. They're not our actual numbers. We got to get the actual, like, so remember the law thing we just did, or what was the last one we just did? I already forgot. What was the problem we just did? Oh, the days. Remember, so, well, it's more like this one. Well, whatever. We've got to figure out the actual number of World Series you would expect to go 4 games. So are you guys track with me? The trick on this goodness to fit stuff is always observed and expected. Observed and expected. You've got to find observed and expected. They'll always give you observed every time. There's the observed because they got to tell you what they saw. That's what they observed. That's what they saw. But what do we expect? How do we figure that out? What do you do with that 2/16? You got to multiply that by something, right? 2/16 is the fraction. You got to take 2/16 and multiply by the total. Remember, just like the 0.5 for the girls, how many girls you would expect? Just like it was 0.5 times 200 total babies. Same thing here. You would expect 2/16 of the World Series to go 4 games. What's the total number of World Series we're recording here? Got to add these up, don't you? What's that? 40, 63, 93. Is it 99?
Yep.
Okay. 99 total World Series recorded there. So you got to take 2/16 times 99, which is, I don't know.
12.375?
Yeah, 12.375. So that's what goes right here. 12.375. Now the next spot, you get how you do this?
Wait, how do you?
That's how many we expected. So I took 2 divided by 16 times 99. Remember, it's percentage times total.
Fraction in these calculators.
Just divide. Just go 2 divided by 16. You just do normal division. So 2 divided by 16 times 99.
Way across and then add them all together. Is that what you're saying?
So I got till I got the 99. I just added all these together to get the 99 total World Series. And then I'm multiplying each of these fractions times that total. Yeah, so the next one, I'll take 4/16 times 99.
So the
the observed is what we add all together.
Yeah, like all those, like,
The observed total,
Those are total.
the total observed is what we add up. Yeah, is that we add up. And then we take that number, a total number, and we multiply by each of the fractions because that's what we would expect.
Okay.
We were expecting 2/16 of all the series to end in 4 games. So that means multiply. Of is always multiply in math. So that's going to be 24.75. Next one will be 5/16 times 99. Whoops, what did I do? I'm getting 30.9375. And then this one's also 30.9375, right? So put those into L1 and L2. Okay, so we all got, what's the degrees of freedom on this one? Degrees of freedom is n-1. People with the TI-83 don't even have to worry about that. It's number of categories. How many categories do we have here? 1, 2, 3, 4. Minus 1, so degrees of freedom should be 3. Here's what I got. I got a chi-square of 5.727? 727. And then the p-value, I got 0.1256, or 57, I guess? 57, yeah, rounded to 4 places. Okay, so what does that mean? Yeah, that p. So the null, remember, is that the data fits, and the H1 is it does not fit.
Is it always going to be like that?
Yeah, for chi-square goodness of fit, it's always fit, not fit. Yeah, so that's nice. Don't have to worry about anything else. It won't ever change. Yeah, put that right in your 3x5 card for the test in a week. For goodness of fit, it's always that. Fit, not fit. Okay, so yeah, so the P's high. P is not low. So the HO does not go. We keep the HO, right? We keep the HO, which says the data fits. The data fits.
Is weak evidence?
It's weak evidence. It is weak evidence. But it seems like the World Series are kind of going like you'd predict, which means those teams are pretty equal. That's what I was saying in the beginning. They're all pretty equal in baseball. The best teams win just over 50% of the time, and the worst teams lose just over 50% of the time. And the best hitters get hits just over 30% of the time, and the worst hitters get one less hit in 10 bats. Yeah, I don't know. Let's see. Failed to reject. There is, no, isn't it B? Insufficient evidence.
No, that's reject.
Oh, well, let's reject. Thanks. What am I doing? Oh, yeah, it's D then, huh? Failed to reject. There's insufficient evidence. Yeah.
Since there's, you keep in know that there's weak evidence.
Yeah, weak, exactly. Weak evidence. That's right. We good? That making sense?
Yeah.
That's the hard part. I think if you got the expected, everything else will fly. So on number 4, they're talking about horses and races. Did they just run the Kentucky Derby? It was just ran, right? We're in the season now. So they're doing the list here, and they're saying you have to look at the claim. What is the claim? Look for the word claim. Test the claim that the likelihood of winning is the same. So it's just like the police problem. They're saying all the days should be the same. Remember, we just added them up and divided by 7? They're saying all the positions on the race course should be the same for the various horses. For the various positions. I'm sorry, the 10 different post positions the horses can race in. So that means you just need to take the total for each one. Got to add all these up and divide by 10 because there's 10 different categories. Just like for the police problem with the days of the week, we took the total and divided by 7. So that is how you will calculate all your expected numbers. That's what you would expect if the horses, if it makes no difference what position the horses run in, you would expect the same number of victories from each of the different positions. So add them up and divide by 10. Just like the police problem when we added up the total days divided by 7. See how that's the same? Whereas this World Series problem we just did, they gave us specific fractions. And so we multiplied those by the total. That's what they were expecting. Okay. So here we are in number 6. And birth records categorized by what day of the week babies are born. All right? What's their claim? It's all about the claim. What are they claiming?
Equal frequency.
Claim that the births occur with equal frequency. Same. So what are you going to do for your expected numbers?
Add them all together, divide by 7.
Total divided by 7. They're saying same number of babies born Sunday, Monday, Tuesday, Wednesday, Thursday, Friday, Saturday. So just take the total, divide by 7. Does that make sense? When they say same or equal, you just add them all up and divide by how many categories. And that'll be the same number for every expected. All the expected numbers will be the same. Your L2 list will be the same number every time, won't it? That's what you're expecting, that they'll be the same. All the rest of the test works out just like the others. An investigator analyzed the leading digits from 790 checks issued by 7 suspect companies. The frequencies were found to be, boom, they list them there. And those digits, check if Benford's law. So Benford's law, again, is giving us the percentages. So this is not same. We're not trying to say they should all be the same. We're trying to say they should fit, not with sameness, but fit with Benford's law. So what am I going to do to find my expected numbers?
Add up all the actual.
Yeah, get the total. Do they tell me? Oh, here it is, 790. So the total is 790. It's nice, they just gave it to me. So then for the first category, we would expect, if these checks are on the up and up and there's nothing funny going on, then we would expect that 30.1% of all checks should have a leading digit of 1. So let me make sure. I want to try to give this to you in a way that makes sense for you. I think you'll remember it way better that way. Do you guys see why we're multiplying this way? Do you know that of means times in math? Whenever we say of, that means times. So if we're saying we expect, if Benford's law is being followed, and there's no funny business here, we expect that 30.1% of all the checks should have, a leading digit of 1. So that means 0.301, we got to change that to a decimal. Of means times. All checks, that's the total, 790. Get your answer. Is that making sense? So you just multiply each of these percentages, when you change them to decimal, times 790. Because you're expecting each of those percentages of the 790 checks to have whatever leading digit. The rest is the same. Can I go ... and move on? Are you okay with that? I used to hate that when my math teacher said etc. and didn't do the problem, but I feel a little differently now. Is that okay, though? I don't want to say ... when you're really not following me. Is that good? So the first, maybe I could do 2 of these. So the first one, that's supposed to be 7. So it'd be 0.301 times 790. So the first one would be what? 237.79. The second category, so that would go, where would that go? That would go right here. 237.79. Now the next one, the second one is 17.6. So 0.176 times 790. Because we're expecting 17.6% of all 790 checks would have a leading digit of 1. That should be 139.04 checks. That's how many checks we would expect to have a leading digit of 1 if Benford's law was being followed. And that's what we're going to try to test. Is this following? Is this fitting? Is there a good fit with Benford's law? If so, you'd expect 139.04 checks to have a leading digit of 2, etc. Is that okay? You just crank out all those. That's your L2 list. The observed is your L1 list. Do the rest. Leonardo?
Is there anything that's going to switch up from this to the next section?
Yeah. The next section is 2 categories.
Oh, okay.
Huh?
If so, why would we have another section? We good there?